Hello, folks. This is Lab 6, and we are starting the concept of shell elements in finite elements, and specifically, we're using Catia V5. Now, uh, the, I will be doing the same problem that you see there in the first four activities. I'll be doing this exact same problem, except that with different ways of uh, creating the model. What we have here is a folded sheet metal, you can see that, with a thickness of zero point 0.1. The bottom edges are clamped and the top is subjected to a pressure of 100 psi. Now, uh, since symmetry is an essential part of finite elements, in every problem that I do, generally speaking, I use as many planes of symmetry as possible. In this particular problem, there are two planes of symmetry. In other words, all I need to do is to create a quarter of this geometry, which is what is shown on the right, and measure it with shell elements. Now, the other thing is that in this particular activity, I'm going to uh, create a box with the size that you see here on the right hand side, namely 2" by half an inch high and 1" width. I'm going to make a box and then extract the top face and the side face from it. Now, in the other activities, I generate the same surface different ways. For example, I can draw an L and extrude it directly as a surface without the surface extraction. But I start with extracting the top surface and the side surface, okay? And let me also remind you that when you have a problem like that, you should realize that it really has to be solved with the shell elements, okay? All right, uh, let's go ahead and do this. On this face, I'm going to draw a rectangle, which is 2" by 1". So draw a rectangle 2" by 1". This is going to be 2", and this is going to be 1". Say OK, exit, and then pad it by half an inch. So this is going to become the box that I was talking about. It's 1/4 of that geometry, but I'm going to extract these faces. So for example, let me turn this thing around so you can see it better. Now, as soon as, what do we actually apply material to this thing? This is made out of, according to the problem description, it is made out of yellow brass. Okay, so let's go ahead here under metal, see if we can find yellow brass. Or yellow brass right here on that part. Say OK. Now I'm going to extract these surfaces. Now once you say surfaces, it cannot be done in part design. And there are two ways to do it. One is to go to one option is to go to start mechanical design, wireframe and surface design. You can see the features that you want there. The other option is to go to shape, generative shape design. So let me do that here. And let's find out where the extract icon is. Let's see now. Look for it. Let's see more. It's right there. You see that? Uh, First of all, let me see what the name of this toolbar is. Operations. And if you look at the third one from the left, there says extract. Now, when I say extract, if I do this window closes. See that? I can do multiple extraction. It won't do it. So if you want to do multiple extraction, you can pre-select both of them and then say OK. Or you do it twice, basically. So where's the extract? This, and say OK. And I can hide this uh, geometry, hide that block. The block is in the hiding. I cannot delete it because this extraction is using that. Therefore, we just leave it the way it is. Now, the other thing is that if these surfaces are the same thickness, I'm going to join them. I'm going to join them. And when I apply a thickness to the surface later on after meshing it, because it's joined, it's going to take the same thickness for both. And of course, there are different ways. There is the local 2D property that you can go to and change the thickness of one of these if you want. And that's one of the activities that we're going to do later on. So basically, we join them, and the sole purpose is make sure that later on when we mesh it, we don't get duplicate nodes along the edges. Okay, so we're pretty much done here. Let, let's go ahead to analysis and simulation, generative structure analysis. Fancy meshes can be done in the advanced meshing tool, but we're not going to do that. Notice that because there is a block that is in hiding, what Catia does, it sees a block and it immediately meshes it. So I'm going to say, okay, but that mesh is totally useless because you're not using a three-dimensional elements. So I'm going to delete this. This has no purpose here. And the only reason it came about is that Katia saw a three-dimensional object and he immediately meshes it. And there's also a 3D property here, which is associated with the element that you just deleted. So I'm going to delete this also. Okay, good. The block is still is in hiding right there, but it's not, meshed. Let me change the rendering here so you can see it better. This is the ivory color, which represents the surfaces. Okay. Now, the meshing has to be done by us. Just like we meshed beam elements, we have octree triangle surface mesher right there. You click on it, and because we joined it, when we select this, both of them are going to mesh at the same time. Because they're joined together, you have the linear option, parabolic option. So let me use the parabolic option, and that thickness, I'm going to make it a little bit smaller, 0.1. Good. If you want to see the mesh, right click, mesh visualization, say OK, and there we are. Okay. Now, if you had not joined these, then there would be duplicate nodes on both sides. So for example, look at this. When you go to the top part, it says nodes at the seam 17, 370, and 18. When you go here, you get the same nodes. Okay, good. Deactivate this. All right. Now we have to give this thing a thickness. So you go to the, just like you did beam cross section, we defined it here, 1D property. We have 2D property. You click on it and you select the surface. Because you joined it, it takes an identical thickness for both of them. And it picked the correct material. But the thickness that I have based on the description of the problem is 0.1 inch. So I'm going to change that thing to 0.1 inch and say OK. All right. Now, don't forget to save. It's the same story, file save management. You save your part, you save your analysis the usual way, and this is important. Don't mess it up for the test, please. I'll leave it to you. We have done 5 weeks of CATIA, so you are familiar with these things. This bottom edge is clamped, so we clamp the bottom edge. And this is a planar symmetry, or you can use the other one. So these two edges lie in a planar symmetry. We use the plane to cut it, and this edge is also lies in the planar symmetry. So let's start with say okay, and for the symmetry we have to go to user define. Let's uncheck everything. These two, this edge and that edge, lie in the YZ plane. Therefore, there is no displacement in X Immediately, rotations opposite. Just like the rule that we had for beams. And user define again. Let me uncheck all of these. This edge lies in the xz plane. Therefore, immediately no displacement in y. Okay, no displacement in y. Rotations are exactly the opposite. On top of this face, there's a pressure. There's a pressure icon on that. And because it's 100 psi, but it's not negative because it's pressing on it, and say OK and OK. Good. And then we're going to run it. Done. So look at the deflection. We can animate. If you look at the displacement, there we are. Let me change this thing to average ISO. Change the material, change the rendering to material shading right there. This is the displacement. Needless to say, uh, this is the free edge. Therefore, that has the biggest displacement. Okay, and you look at the von Mises stress. There we are. Obviously, big stresses around the seam, and also big stress here because it deflected the most. Now, of course, if you're doing this thing for living, then you would like to look at the magnitude of the von Mises stress. Make sure that it doesn't exceed the yield strength and things like that. But we're not worried about it in this particular course. So that takes care of activity 1.